Hare Krishna. Now we are going to see how to apply the Bellman Ford algorithm. As like the Dijkstra's algorithm, this Bellman Ford algorithm is meant for finding the shortest distance of the source node from every other node of the given graph. Here the graph with 4 vertices has been given to us. From the graph we can decide the adjacency matrix, which is of 4 by 4 size, since 4 vertices are there in the given graph. The first step from the Bellman Ford algorithm is to list all edges in any order along with the source node, destination node and its weight. So here from the arrow we can figure out which is the source node and which is the destination node. So as it is, this arrow is originated from the A. This A is acting as a source node, whereas B is the destination node and its weight is 5. So this is how all the edges have been listed here. The second step is to initialize the distances for all these vertices. So the distance infinity is not representing the largest distance. Instead it is representing that this distance is unknown, means which is to be calculated. The next step is to select the source node. Here A has been selected as the source node and that's how its distance is set to 0. So this is how we get the distance 0 for this A node, and for remaining it is infinity. Next step is iterative in nature, where we are going to consider all these edges for v minus 1 times. Since we have 4 vertices, we are going to repeat this process of considering all edges for v minus 1 times, that is 3 number of times. The reason I will explain soon. By considering the edges, basically we are updating the distance v, where node v is reachable from node u, and its distance can be updated, that is distance v can be updated with the formula distance u plus weight of the edge which is connecting this u and v. Okay. So and for updating this distance v, it should fulfill these 2 conditions. First one is that distance of u should not be infinity. It makes sense. See this example where v node is reachable from u. So if the distance u is known, then only distance u plus this weight of this edge could give us distance of v. So if this distance of u node is unknown, we are not able to calculate distance of v. So say we want to go to Mumbai from Kolhapur via Pune, and if we don't know the distance of Pune from the Kolhapur, we are unable to calculate the total distance from Kolhapur to the Mumbai. So this is how this first condition makes sense. Second one is that the current distance of the v node should be greater than newly calculated distance, and newly calculated distance is distance u plus weight of edge which is connecting this u and v. So now we will proceed with the iteration 1. So with this iteration 1, we are going to consider all these edges and will use this formula in order to update the distance of v. So with the edge, first edge AB, A is the source node and destination node is B. So if as distance of A is not infinity, it is 0, we are able to update the distance of B. So how to update this formula? Here we have to substitute the values of B and A. So distance B is equal to distance A plus weight of this edge which is connecting A and B. So it is 0 plus 5, 5. So this is how this distance of B has been updated. Next edge which is to be considered is AD. So distance of A is 0 and D is reachable from A, which is this D is reachable from A through this edge AD, which is of weight 10. So 0 plus 10, 10. This is how the distance of D has been updated. Next one is the BC edge. with BC edge, this since the distance of B is not infinity, we are allowed to make change or update the distance of C, distance of B plus weight of BC. So 5 plus BC is 3, so 5 plus 3 is 8. So that's how the distance of C has been changed. Next, CD edge. CD is of weight 1, so distance of C 8 plus 1 9, and this 9 distance is less than previously held 10. So this 10 has been replaced by 9. If we continue with the second iteration, we are going to get the same output. Okay, we'll discuss it also. For AB, distance A is 0, so 0 plus AB is 5. So that's how distance of B will become 5. This newly calculated value matches with the previous one, so no any change will occur here. For the AD also same happens. Here distance of A is 0 and this weight of AD is 10. So it is resulting into the 10 value, but with first iterations output, it is clear to us that it is holding 9 value. So 9 is less than newly calculated 10 value. So this distance is not going to be changed. Next, considering this BC, distance of B is holding 5 value, BC is 3. So that's how distance of C becomes 8, and rightly also it is holding 8. So no any change will occur. Lastly, by considering this CD edge, distance of C is 8, 8 plus the weight of CD is 1. It is resulting into 9 value, and it is rightly also holding the same. So no any change will occur. So the again, when we continue with the iteration 3, we get the same output. Now the question arises, with first iteration itself we reach to the answer, or we reach to the shortest distances of BCD nodes from the A node. A is treated as the source node. B is located at 5 distance from A, which is the shortest. C is located at 8 distance from A, which is also the shortest distance, and D is located at 9 distance from A, which is also the shortest distance, considering this graph. See, D is reachable from A through 2 paths. Here direct path is available, which is of distance 10, whereas by following this path A to B, B to C, C to D, it results into 9 value, and that's what we obtained here. Okay. C is at distance 5 plus 3 from the source node. Total distance is 8. B is located at 5 distance from A. So that's how we obtain the shortest distance for this BCD nodes from the source node A. Now question arises, why to consider all these edges for V minus 1 times? Simply, why to apply this algorithm for 3 times or V minus 1 times? So this is the reason. In case of any connected graph, for any 2 vertices in a graph, the shortest path between them can have at most V minus 1 edges. So see, this is the graph with 3 vertices. So C vertex is reachable from A through through this edge AC. But if we consider the longest path, then the C lies at 2 edges apart from this A. Now 3 vertices are there and C is at distance 2 edges apart. So at most V minus 1 number of edges could be there which may give us the shortest path. So this is also the best example where D is reachable from A with two alternative paths. Here this D is present at one edge distance apart as well as three edges apart. Okay, but these three edges are providing us the shortest distance. So in the first iteration itself, some shortest path might be found, but considering the edges for v minus 1 times, this Bellman Ford algorithm guarantees that all possible shortest paths are correctly identified, have been considered, and accordingly the shortest distances of all the nodes from the source node have been obtained. Why this Bellman Ford algorithm involves v minus 1 iterations, that will be cleared with this example. Now earlier we applied the edges in order AB, AD, BC and CD. Now this order has been changed because there is no any specific order in which these edges are to be selected, and then to calculate the distance of V based on the distance of U, where this edge is connecting this U and V. Now we are changing the order of these edges. With iteration 1, we are going to follow this order. The first edge we are going to consider is the BC, second CD, third AB and fourth AD. So with first iteration, BC edge cannot be considered because the distance with BC edge, B is the source node and C is the destination node. And in order to update the distance of destination or V node, the distance of U node should be known. And here B is infinity. So we cannot consider this edge. Moving further, we come across this CD edge. Now with CD also, the distance of C is infinity. So again this will be ignored. Then we will move further with AB. Now here in case of AB, distance of A is 0. So that's how we are allowed to update the distance of B based on distance of A. Distance of A plus the distance of or cost of this AB edge, which is 5, the distance B could be updated. Okay. Similarly, the distance of D node could be updated to 10. So that's how this first iteration is over. So that is what said earlier. In the first iteration itself, some shortest path might be found, but considering the edges for v minus 1 times, this algorithm guarantees that all possible shortest paths are correctly identified. So here in first iteration, we have obtained the shortest distance of B, but still we have not reached to the shortest distance of D. So here the order of edges matter, and as there is no any specific order in which these edges are selected and are processed, so hence we have to repeat this procedure for v minus 1 times. Okay, so that we will get the assurance that we will all the v minus 1 paths have been checked, confirmed, and accordingly we reach to the shortest distance of all nodes through the from the source node. So with second iteration, this BC edge is considered, for which U is B and V is C. So distance of C could be updated based on distance of B. Now distance of B is 5. 5 plus BC, weight of this BC edge is 3. So that's how the distance of C has been changed to 8. Next, considering this edge CD, so distance of C is 8. 8 plus CD is 1. 8 plus 1, this how this distance of D could be updated. Now the newly calculated value is 9, whereas previously it is rightly it's holding 10. So this 10 could be replaced by 9. Considering this third edge AB, distance of A is 0. 0 plus cost of AB is 5. The newly calculated distance of B is 5. So it matches with the previous value, so no any change occurs here. Next, distance of by considering this edge AD, the distance of D could be updated, as distance of A is not infinity, it's 0. 0 plus distance of AD, which is 10, it becomes 10. But as distance of D is 9, which is less than newly calculated value, this value is going to be retained. With the third iteration, again by considering this edges in the order BC, CD, AB, AD, it not making any difference compared to the iteration 2. So we get the same output. So that's how this Bellman Ford algorithm is finished. With the next video, we'll see how is it different than the Dijkstra's algorithm.